Good afternoon. My name is Matt Elgin. I'm the European Market Lead at Upstream Tech. I'm based in Basel in Switzerland. I have a background in geospatial systems and hydrology, renewable energy and technology. And I've been fortunate to work across New Zealand, my native New Zealand, Australia, Singapore, and more recently here in Europe. I'll hand over shortly for Dirk to introduce himself. But firstly, just a couple of agenda items and some housekeeping. So for today's session, we're going to cover some of the particular challenges, both in terms of policy and climate, that are affecting the European water management landscape. And then we'll cover some innovative solutions from both KISTERS and Upstream Tech that we've used to help clients solve some of those challenges. And then we'll hand over for some Q&A to the floor. So just in terms of housekeeping, if you're not familiar with Zoom, there's a couple of key points I just wanted to raise. We will be recording the webinar, and you will get access to a copy of the recording afterwards. The second thing I wanted just to point out is, if you're not familiar with Zoom, there is the option to add captions, auto captions in the language of your choice. So feel free to make use of that if you need. And then finally, the Q&A option, which is also at the bottom. Please feel free as we go through the webinar. If you have any questions, just type them in there, and we'll do our best to answer them at the end or after the webinar if we do run out of time. So firstly, just a little bit about Upstream Tech. We build software tools to accelerate the pace, scale, and impact of climate solutions. We have a team of 35 people, and we take an interdisciplinary approach to solving climate problems. Our experts include software engineers, AI and machine learning specialists, geospatial scientists, and hydrologists. HydroForecast is Upstream Tech's AI hydrology forecasting solution. It's been deployed in more than 15, I think now about 17 countries at last count, including eight countries in Europe. Our clients in Europe include renewable and hydropower leaders, such as ENGIE and Landswerken, and it's great to see that we've got a few folks from their teams on the call with us today. HydroForecast supports multiple languages and is compliant with European data sovereignty laws and guidelines, so can be deployed anywhere worldwide, including here in Europe. I'll now hand over to Dirk to introduce himself and the KISTERS group.
Hello, everybody. So a warm welcome from the KISTERS side. I'm Dirk Schwanberg. I'm head of the business unit HydroMet. And as you can imagine, that's mainly about hydrology and metrology now. KISTERS in total has about 800 experts across 13 companies on the global scale. So different backgrounds. So my personal background is civil engineering with a focus on hydrology. And I did quite a number of implementations of forecasting systems in the past. So they didn't get me in as a manager. They got me in as an expert for forecasting systems. On the other side, there are a lot of IT specialists and technicians around at KISTERS just implementing hydrometeorological database systems. So that's the core of the company. And so in that sense, we are the ones working broad on the integration of hydrology and metrology data. And that's something we do in about 60 countries around the globe. So right now, data becomes more and more important. Organizations are working in the domain hydrology, always kept, of course, their data clean to do statistics and so on. But I think data becomes more and more important, and we have more and more opportunities to work with this data nowadays. So let's go for the next slide, Matt, please. On the next one. Okay, now what's going on? And I start quite broad here. Yeah, weather extremes, that keeps us all busy. on one hand. That's one side of the medal here. I mean, finally, we bring it back to forecasting systems and why we need forecasts. Of course, early warning is an important issue, and just have a look at some recent floods here. The one in Germany in 2021, what happened in Spain last year in the Valencia region, but also recently in Switzerland, landslides and so on. So that will unfortunately continue this way. On the other side, also droughts as an extreme, not um, as much in the news as the floods when they occur, but more like also like a quite damaging, long-lasting event in some regions across Europe. On the other hand, when we talk about water management and also energy management, forecasts can be interesting for managing extremes more like on the energy and water resources side. So this could be about low water levels, for example, the ones we had in the French Rhone or Rhine rivers in Germany. That has an impact on navigation. It has an impact on energy supply and so on. And so somehow this is all somehow impacting us. So let's go for the next slide. As you know, if you are somehow engaged in water resources in the European Union or even outside, there's an impact of the EU regulations as well. Water Framework Directive is a quite important cornerstone. That was the first large EU policy on water resources. So that's more like on the health of the water systems. The next one we faced was the Flood Directive. That was issued 2007. So that's about hazard and risk maps and how to manage floods. So that means, like in general, I would say, like water managers must operate in a more resilient, lean, transparently, digitally way, just to adapt to challenges such as climate change, but also other challenges such as like increased use of water and so on. So in that sense, you don't really see an explicit requirement for flow forecasts in this kind of regulations. On the other hand, like forecasts and decision support can serve as a quite important non-structural measure to make better use of your existing infrastructure. So it just gives you efficiency and foresight and helps you to better manage your infrastructure. So let's go to the next one. So as you can see, there's more stuff coming up, and that also contributes. So we see new initiatives coming up, and I just pick up the second one, European Green Deal. We don't know exactly what it all includes, but there's quite some investment into green economy, and of course, a better use of existing infrastructure sounds like a very good measure, and that's where like forecasting systems and the surrounding data management can make perfect sense. Let's go for the next one. So, and that's the core topic of KISTERS, data management. That means that we first need to get the data together and the tools to make sure that the data is of good quality in order to use it, and that it has a proper structure. So just like it's a bit the garbage in, garbage out principle here. So we need to make sure that data is properly maintained before we do a data-driven forecast, for example. So that means that we sometimes see disconnected systems, that data is just hidden in silos within the organizations across departments and so on. And we sometimes help to integrate this data. On the other hand, like data is important to also understand the trend in what the data tells us. So it's like the data is often non-stationary. So weather patterns are changing, but also the way of the water management is changing, or demand patterns of water use are changing, and so on. So on one hand, what we like to do in terms of data management is just help people to move from manual workflows, which are like subjective or error prone, to something more digital. And that's also what the software supports in a broad sense. In addition, if you think of decision making, you may think of like decision making of reservoir release decisions, flood responses, and so on. So that includes uncertainty, and one of the tasks we have here is to make this uncertainty a bit more explicit and reproducible and so on. So let's move to the next one. You can skip this. And this one as well. Okay, so what is KISTERS doing in the field of data management? I think most of you will know. So WSGI is the hydromet database now being around for about 3 or 4 decades at least. That's an important enterprise product. DataSphere is a corresponding counterpart in the cloud. So both manage data, both use the same principles of processing time series and so on. Both share like the same core of just getting data in, validating the data from different systems, and then processing it, doing data validation, and so on. What you see on the right is just a mix of screenshots from WSGI and WSGI portal applications and the DataSphere on the lower end. So as you can see from the look and feel of the latest graphical user interfaces, it's not that much of a difference. It's just like a different scale of a product. The WSGI as an enterprise solution is more the one that's being used on premise for the larger organizations, and the DataSphere is a good addition if you don't like to host a system on your own, and we operate it in the cloud for you. But there's like a whole transition in between. Let's move to the next one. So just imagine KISTERS as the broad platform supplier for hydrological data, and that starts on the left side with the data acquisition. So we just make sure as well to get your sensor data into a system, regardless if this comes from the sensors directly from loggers, from a SCADA system, if it's a raster data such as radar observations or remote sensing data from satellites, water samples from the labs, and so on. So we can get this all in and give it a structure within the WSGI database or the DataSphere. An important next step is, of course, to make sure that this data is of good integrity. So that means it should be consistent. That means complete, without gaps, and up to date. But it also should have a good quality. So we apply data consistency checks, we apply data validation rules, we do data estimation to make sure that the data is of the best quality possible. And this is both supported in an automatic mode, but also interactively with the user. Okay, now the green part, that's now the interesting part where also the forecast contributes, and that's something Matt will explain us in detail. So what do we need to set up a good data-driven forecast? That's of course data. So that's both historical data and in the operational mode, of course, real-time data. So that's what we supply to the forecasters, and that's in this case what I said. Like Matt will explain in detail what he's doing on their side. So what we do is to make sure that we have a seamless integration with the forecast system. And so that means we send data out, we receive the forecast back. We may implement additional steps on top of the forecast. That could be about decision making. Just think of a reservoir system where you like to mitigate floods downstream. This could be about forecast bulletins. It could be about web dissemination of the results. It could be everything downstream here. It could be about like alerting people and notifying people of whatever threshold crossings. Okay, so that's what we do on the KISTERS side. And again, we somehow embrace the forecast itself. And now Matt will give us more details on the forecast.
Great, thank you, Dirk. Yeah, I think we can't underestimate the importance of that quality input data, and I'll talk a little bit more about how important that is as we go through. Dirk's already touched on the importance of extreme events, but what we're finding on the forecast side is that climate variability is increasing, and traditional models are struggling to keep up. Europe's warming faster than the global average, and as you probably are all aware, 2024 was the warmest year on record. Well, heat stress and temperatures are increasing, but so is rainfall. So in 2023, 1 in 3 rivers in Europe exceeded their high flood thresholds, and 16% reached the severe 1 in 20 year flood extreme, according to the ECMWF. Combined with that, we're seeing glacier ice loss, variations in precipitation, where perhaps snow would have been falling. We're now seeing rainfall at later in the year and at higher altitudes. All of this is contributing to increased variability and new runoff patterns. Timing of inflows is changing. Volumes overall are increasing, and as Dirk highlighted some significant events. I mean, we really only need to look in the news in the last few days in Ireland and across Europe to see the extreme events that are occurring. So with that change, we're seeing increased challenges for water managers, and that's really across all sectors that we work with. In flood management, obviously, but also anyone who's trying to optimize water for domestic supply, irrigation, power generation, energy trading, and dam safety, all are experiencing increased challenges. Enter Upstream Tech's HydroForecast. So HydroForecast is a hydrology model that uses a combination of global data sets and local observed flow to create a probabilistic forecast of inflows into dams, rivers, and reservoirs. And we can do that for, as I mentioned earlier, for any basin in the world. These forecasts will tell us how many cubic meters per second will flow into a specific point over a given period of time. And we can offer both a short-term forecast that's on an hourly basis for sort of roughly the next 2 weeks, and also an annual version of the forecast that can provide daily inflows for sort of 90 days all the way out to 1 year. Under the umbrella of artificial intelligence, HydroForecast is a machine learning model, and more specifically, a long short-term memory, LSTM model. We've trained that model on stream flow and weather data from a diverse set of over 500 basins from across the globe. So the model has learned how all the different inputs interact with each other in the real world. And that's not how a traditional physical hydrology model works, but it's been a contributing factor to just how we're able to outperform the status quo with this model. So how do we go about it? Well, we start with the best available input data. So that's typically a combination of weather forecasts, the kind of information that Dirk was just discussing, your own data. So any in situ measurements, flow measurements, any data. Obviously quality is key. And so when we work with KISTERS, we get some really good benefits from that platform. Once we've got that data, we do a site-specific tune of the model for your catchment. So that's combining data sets in terms of historic data that you might have, and anything that we can do to define the characteristics of that catchment. And the result is a accurate probabilistic streamflow forecast. But as I've already mentioned, one of the key benefits is this model can learn from outside of the local experience. It's particularly strong as a result in extreme events. The ones that maybe don't exist in your training data, but probably are starting to happen more and more frequently. So as an example, imagine the soil moisture is at an all-time low in your catchment in France after an exceptional summer drought like the one we've just had. A large autumn storm is predicted. It's warmer than usual, so rain rather than snow falls at much higher elevations. What's predicted isn't something that's been experienced in the catchment before. Typical physical models will struggle to accurately predict the inflows and the resulting flooding. However, our model includes training data from basins and sites in places like the southwest of the United States, places where these conditions are experienced frequently. And so the model knows exactly what's likely to happen because it's seen similar conditions elsewhere. And that really kind of ties into the key advantage that we see with our model. You know, we're building off traditional physics-based approaches. We're providing benefits that you don't see in off-the-shelf AI models. And the result is that it's really a first of its kind large AI model that is, you know, theory guided and can take advantage of the benefits of both those two physics and AI model learning approaches. So when you see, for example, you know, the ability to utilize multiple weather forecasts, which is obviously one of the most variable inputs and the one that can provide the most variable results, you know, that's a key advantage that we're able to offer. So we can take multiple forecasts, compare them, and use them to produce the probabilistic output. We can operate even when data is missing. So if a gauge is washed away in a severe event, we can still continue to provide a forecast. The output is physically realistic, just like in a physics-based model, but unlike an off-the-shelf AI model. And again, as I've mentioned, yeah, we can learn from outside the historic record, which is also a key advantage that we can offer. So we're bringing it all together with a seamless integration with KISTERS. It gives you a common platform for your tools and your data. We're able to provide a seamless hydrology solution. For example, for a shared client, Wasserwerk, we've been able to deliver a solution that's been particularly effective in capturing their complex hydrology processes rather. So we've been able to identify when discharges were delayed due to soil moisture changes. We've been able to provide more precise predictions of rare or unknown events in those catchments. Again, because of that multi-basin training. Overall, the result has been a seamless integration and models that reduce the risk for our clients despite the changing policy and climatic landscape. Thanks for listening, and we'll now take your questions. I'll just going through the questions. So question here from Brett. Does HydroForecast work for ungauged locations? Yes, we can work in ungauged locations. Obviously, the more input data we have, the more accurate the forecast. But in a situation where there isn't gauge data available, absolutely, we can function in those locations as well. Just looking through.
I can take the next one.
Yeah.
So there's a question about, because it's about AI. So I'm a bit neutral here, maybe. What is the general level of adoption of AI technologies in the hydrology community in Europe? Is there excitement, concern? I think like hydrologists are more on the conservative side of the people we know adopting AI. I think if you start to try it, you will see the benefit. Now, like, I would not don't consider it necessarily like a replacement of what you're doing right now. It's more like also of an addition, and then that's important to get some trust and understand how it works and what it provides to you. We see that it's now started getting used. It's definitely in an early stage in hydrology. I think where it's being used a lot is definitely hydropower. That's about just like hydropower assets, and the increased efficiency of a hydropower scheme by a percent that makes delivers a lot of money. So I think that's where people are most open to this kind of approaches, and that's also where it's being used most. In the classical forecasting agency, I think it's at an early stage.
Yeah, I guess I'll just add to that. What we are seeing with a lot of customers is that they will use our forecast alongside perhaps the traditional physics-based model. And it might be that one is, better in one situation than another. And, particularly as I mentioned, the extreme events are something that the AI models are particularly strong at picking up. So HydroForecast does well in those situations. I think too, I would say if you talk to people even 2 years ago, there was a lot more concern than there is now. I think people are starting to see the value of these models, and there's growing evidence of their performance. I guess is key, and an understanding of how the inputs relate to the outputs as well.
And also think I mean, like most organizations doing hydrological forecasts use different weather models. So in that sense, it's just like a parallel approach. It's also a good idea to use different hydrological models to get a bit of a variability. And one model will be good in one aspect, and the other one has different advantages. So it's always good to have a range of options here.
Yep. So the next question we have here, how does HydroForecast adapt to climate variability? Is there much calibration or retraining that needs to take place to account for changing climatic patterns we are seeing? Great question. Look, there's sort of two threads to this. On the one hand, the model learns from its own experience. So there's less need than you would have in a physics-based model to retrain. The other point is that the retraining process is much, much easier than you would find in a physics-based model. So we do recalibrations and things on models when it's required, and that's all taken care of by the Upstream Tech team. So it's relatively lightweight, particularly for our clients, but also for our team, compared to what you would see with a physics-based model. Okay, so how would a LSTM be embedded in a digital twin using microclimate data and subcatchment watershed for a seamless hydrology approach to adaptive asset management? So we obviously can take in any climate data that you may have. We typically divide the catchment up into subcatchments, so we can certainly manage each of those individually. In terms of an approach to adaptive asset management, it definitely is something that we've done and we've seen done in hydropower, for example, where say run of river assets, clients are looking at when the right time is to take those out of production to perform maintenance, and using the forecast to help guide those decisions and that timing. I'm not sure if that fully answers your question, Jonathan. So feel free to get in touch with us after. We're happy to discuss that in more detail. So if you want to calculate we use HydroForecast to calculate a flood event. Is it possible? Yes, is the short answer there. So we're frequently used as an input to flooding models. We're providing a flow level. But for instance, we've got clients in New Zealand who are using our model as an input to flood forecasting. So yes, we definitely can contribute to flood event management. Another question: how do we contribute, or how do we handle river systems with cascading hydro stations? Yeah, this is something that's obviously a complex thing for any physical model of the landscape. You have for those of you not familiar, the scenario is, of course, you've got a dam, water gets trapped behind the dam and released on a schedule designed by humans, not by nature. It's definitely something that can be handled. We can also handle pipelines and other, man-made interactions in the environment. What we tend to do is work with the client to work out the best way of modeling the outflows from those environments. If you don't know the outflow, which can be the case, perhaps if it's a competitor who has a dam upstream in a hydropower market, the model will start to learn typical approaches. Now, it's not perfect, but if there's a diurnal pattern of releases from that dam, we'll see those. If it's, say, for irrigation and there's seasonal patterns of release, again, the model will see those seasonal patterns and see those inflows and start to understand what's going on. So again, an AI model has some advantages over a physical model in a situation like this. So it's sort of, I guess, the long answer to the question is really, it depends. If you have access to the data, we can certainly incorporate it. And if you don't, we can try and model it from past experience.
Yeah, I may add, like, in addition, I mean, if you're looking for an operational model to do decision support on the reservoir releases, for example, during a flood event, or to maximize hydropower revenues, that's the classical domain of optimization models. You would just add downstream of the inflow forecast, and where you just consider different release trajectories, different power generation trajectories, optimized for revenue by taking into account the price forecast and this kind of things. So that's a classical interactive type of model we integrate into forecasting systems downstream of the inflow forecast.
Yeah. Is there a minimum and maximum area that can be modeled? Short answer to that is no. We have some very small catchments that are being modeled for some clients right now, up to huge basins. Columbia River in the US, for example, the Rhone here in Europe. So there's certainly no maximum. When you get to smaller basins, we do, I guess, have, when we're using remote sense data, there are, you've got gridded data sets that have quite large, sometimes cells. So in terms of area, you can lose some of the granularity in a very small basin, but the more input data you have in those situations, the less that becomes a problem. But in short, yes, we can work in any size basin. What are clients currently doing most with these capabilities versus what is emerging in practice? So I think if I talk about the use cases, we've got clients using our solutions in production for reservoir management, whether that be irrigation, urban water supply, hydropower. So all using it in practice. I think the emerging areas for Upstream Tech are really around new areas of business for us. So you have a small number of clients, for example, using it in tailings management and mining. But that's probably more to do with us, in terms of what markets we're entering. I think, I guess if the question is it production ready? The answer is absolutely. It's being used in production for reservoir management, for flood management, and various other applications as well. Once set up, how much effort is there in continuous training of the approach? Can this be automated? In short, we do validation on the model on a regular basis at Upstream Tech. So we will, when a client signs up for our service, we provide a regular validation, usually annually, sometimes seasonally of the model. But in terms of continuous training, there's really nothing required. We're more or less validating that the model is performing well. So rather than training the model per se. So there's not really a lot of effort involved in keeping the model running. Hopefully that answers your question, Michael. Have the models been tested for long-term forecasts, say up to 5 years? How about models performance for regulated watersheds? We've done backcasts to check the model performance against actuals for, I think, in some cases up to 20 years of data. So in short, the answer is yes. We frequently do that kind of validation for clients to give them confidence in the performance of the model. So in short, we can provide some data afterwards. Feel free to reach out to me. I can give you some information about I haven't got a name on the question. We can give you some information about the performance in regulated watersheds with some specific examples. So a question from, I assume from the US, asking, are we able to leverage new observational data sets, such as LiDAR snow measurements in Western US watersheds? Yeah, again, I think the longer duration that we have, obviously, the better that is, but we frequently have clients who maybe only have a small number of years of input data that we can utilize. In terms of SWE data, that's something that we're working on at the moment in terms of incorporating that into our models. So it's something that we're adding, I guess, as a feature, as an input to the model. But the model itself can also forecast the SWE. Obviously, the snow is a combination of precipitation and temperature. So we do intrinsically has an understanding of the SWE in those catchments as well. But again, happy to discuss that in more detail offline. Another question, how many times a day is the forecast updated? Did you use basins in tropical countries to train the model? It's a very diverse, so to answer the second part, it's a very diverse bit of catchments that have been used to train the model, from subarctic to tropical. So a very broad set of catchments, in short, so yes. how many times a day is the forecast updated? We typically use the weather forecasts that are fed in to determine the update cycle, but we can do an hourly update. Now, sometimes those weather forecasts may only be available several times a day, but we can do up to an hourly update of the forecast based on whatever the latest input is that it's available, and your flow measurements and things that may have come from KISTERS or another platform. Question here as to how the hydrologic models account for micro downbursts at a municipal level. So it's obviously a difficult thing to forecast. At the moment, we typically use publicly available weather data to forecast inflows. And yeah, there is situations where the local climate and meteorology mean that a burst happens here and isn't detected by the model. One thing that can help with that, though, is the fact that one, if you have measurements on the ground, so if you have your own gauges, again, perhaps fed through KISTERS, that can help us forecast. The second is the fact that the model is probabilistic means that for some of our clients where they're trying to forecast floods in an urban environment like that, they will tend to utilize say the 75th percentile to predict the risk. So again, having a probabilistic forecast somewhat offsets the fact that you may end up with some downbursts that are patchy across your catchments. So there are some things we can do to help set up the model to be most useful in that scenario. Just conscious of time. I know we were to wrap it at 4:45. Look, if you do need to leave the call, we will share a recording so you can pick up the rest of the questions. But we'll keep going for a few minutes with the further questions. We'll try and get through as many as we can. But we've got quite a few to go. So we may have to pick a few of them up offline afterwards, I'm afraid. But thank you very much for all of your input. So how does the model change from using short-term inputs like rainfall forecast to longer-term forecast horizons? So yeah, so our seasonal model definitely addresses this challenge. So as most of you probably are aware, the best sort of forecasts run 14 to 20 odd days out. Obviously getting more accurate as they get further away from the current point in time. If you're forecasting 365 days ahead, you're essentially relying on a combination of the experience conditions and long-term averages. So our model kind of gets to this point where it's merging those together as we get out beyond the visibility of the forecast. Again, we've got the ability to incorporate things like in a snow-fed catchment. We've got those kinds of inputs, so precipitation and temperature from previous weeks and months will impact the ongoing inflows. So there are a number of things we can use to help manage that. Again, we could probably talk for quite a lot of time about how we go about this, and be happy to take that question offline as well, so we can delve into it. So again, feel free to get in touch, and we can talk about it in some more detail if you're interested. Jose has asked, to what extent can hydro forecasting systems accurately predict normal, non-extreme flow conditions in highly regulated rivers, and what are the data requirements? Again, as we kind of said earlier, the more data, the better. So if you have any kind of inflow details, if it is regulated, if it is controlled, what releases are happening, all of those help us to improve the forecast. Although if they're not available, we can still make a prediction. The models will still work well in a normal situation. I think, as I kind of highlighted the importance in those extreme events of drought and flood, because other models tend to perform less well. But we can certainly, again, we can jump offline and talk to you about the level of performance we're able to achieve here as well. Are the primary current clients in energy and government insurance corporates? Our client base is quite diverse, but predominantly, it is in energy, government. So every aspect, I guess, of government, from water authorities to environmental agencies. We have done some work in insurance, less so in corporates, but essentially it's across those industries. But really, I mean, the model is applicable to any organization that needs to understand water inflows. So Michael's asked, what does an implementation of HydroForecast look like to a client whose hardware systems are used for training, running, display of results, etc.? Is it implemented as a turnkey solution or through more a partnership approach? So again, like all good complex questions, it depends. We certainly can deploy it as a complete, almost hands-off approach for a customer. So we will typically engage with a client on the hydrology. Our hydrologists will work with you on what's important from the output. I mean, what do you need from the forecast? Do you need a 30-day horizon? What matters? And we'll tune the forecast to those things. In terms of like IT hardware systems, we typically deploy the solution as a SaaS platform, so software as a service. However, we can deploy on-premise for customers if required. And so there's really a combination of different ways we can go about this. Unlike a physical model, the speed to deploy is much, much higher. We're typically able to train the model, get it up and running in 90 days or less. So we're much faster than you typically see in a physical model situation. But we definitely like to work with our clients, and we'll bed that model in, making sure it's delivering what it needs to, validating the performance with you as we go.
And I would like to add to it. I mean, as a team of HydroForecast and KISTERS, we can even put like our sensors on the ground, take care of the data acquisition, manage your data, and do whatever downstream processing. So that's the main advantage of acting as a team of KISTERS and HydroForecast, that we have this whole broad range of options available. So in that sense, yes, turnkey is absolutely possible.
I've got a question here about what benefit does a dam or hydroelectric plant gain by using AI-based forecasting systems? So on that, Solomon, we have we've got case studies where we've improved performance by around 6% in terms of revenue as a result of utilizing our platform. Obviously, all of these things depend on your energy trading environment, on what current models you have and the performance of those. But in short, we're seeing quite significant returns. Obviously, if you're in the energy sector, a 6% improvement on a large hydro asset is a large sum of money. So there's been examples where we've delivered quite exceptional return on the investment that clients have made in the solution.
That means even if you have only 1 or 2%, you have a return of the investment in a couple of months, typically for medium-sized or large hydropower plants.
Yeah, that's right. Matthew Ellison's asked, do we have examples from pumped catchments? Actually doing a trial for a pumped catchment right now, and while I can't share the results with you, we are seeing some really good outcomes for the customer. So that's obviously an open loop situation, but yes, it definitely is applicable to pumped hydropower as well as traditional hydropower installations. I am conscious of time. I know we've got several dozen questions still open. Look, I want to thank everyone for participating and particularly for your questions. I know apologies that we haven't been able to get to all of them. We will do our best to provide some kind of response to those where we've got a name. I know a lot of them are, we don't have the name of the person who's asked the question, but feel free to get in touch with us and we'd be happy to share further. So I want to thank you all for your time on behalf of both KISTERS and Upstream Tech. And we look forward to speaking with you further.